out for the banquet tonight because space is limited. If you have not yet checked out your name on the list out there, either yes, I'm coming, or no, I'm not coming, please do so. It's really the no's that we're interested in, because if you don't check yourself off as no and you're not coming, then we lose out on the opportunity for putting somebody in that spot. Of course, if you don't do anything, if your name is neither yes nor no, you're going to immediately be there. Okay.
Okay, let's start the last session of the day. Our next speaker is Andrew Berger from the University of Rochester, and he's going to tell us about flipping the electromagnetic theory classroom.
Okay. I assume people who are standing in the wings want to be in the wings, but obviously feel free to be disruptive and take a seat. Okay, I've set myself a timer because this is actually the amalgamation of two talks. I send regrets from my colleague Jim Zavislin at the Institute of Optics at the University of Rochester. He was going to come also. He was going to talk about our graduate program. And since I was coming as well, since I was interested in education, I put in a title for a flipped classroom talk. I was just going to talk about the stuff I do there. And Jim had some cataract surgery, and he wasn't cleared to fly. So, and we got sort of combined together. So I'm going to switch in the middle, which is why I'm trying to make sure I don't spend all the time just talking about our grad program. But that's the main reason I'm here. And if there's time, I'll talk about some stuff I've done with Flipped Classroom. So let me, right, of course. That's what I've got to get over here first. Okay, how did that get there? All right. All right. So I'm from the University of Rochester. It's another one of the programs in the country, as you know, I think, that has, in our case, a department called Optics. When you see the Institute of Optics, that's a historical name. Happy to talk with you about that at dinner or whatever. But we are the Department of Optics in the Engineering and Applied Sciences School at Rochester. A beautiful place to live. It's actually our campus is the grounds of an old golf course that was bought in a land swap for us by George Eastman, who was the founder of Kodak and the benefactor of many things at the University of Rochester. I'm happy to tell you much more about Rochester. It really is a wonderful place to live and to work and to be a graduate student for those years. And people were talking earlier about stipends. One comment I'll make about stipends for grad students is that we found that it doesn't matter if you tell people who are comparing our offers to Boston or Palo Alto that it costs way less to live in Rochester. We found that people were giving us feedback that they were very swayed by the dollar sign of the offer. So we sort of have had to participate in that arms race, even though you can sock away a lot more with that, stipend living in Rochester. So, okay, that went the wrong direction. So we're located up here. We are about 6 hours away from a whole bunch of major cities. You probably wouldn't have gotten it right if I told you that we're due north of Washington, D.C., but we're about the same distance from Boston as we are from D.C., so you can get to all these places in about a half day's drive. And it's not as snowy as it is in Buffalo, which is getting all the snow from Lake Erie, or Watertown, which is where it gets all the snow from Lake Ontario. The wind has to blow this way for us to get really hammered. My family lives in Lexington, Massachusetts, and they get a lot more snow these days than I do. So we live in two buildings in the Institute of Optics. Our historical old home is the Wilmot building over here, and it has recently been dwarfed by, in the mid-2000 decade, with a big new building. We occupy the top 2 floors of this, the Gergen building, which the lower floors are for biomedical engineering, which is actually a really cool synergy, which I'd be happy to tell you about as well. I get a lot of my collaborations, because I do biomedical optics from interacting with people on those floors, where I have a secondary appointment, but it's really the fact that they're physically near me. And yeah, that's a pretty building, and it lights up well at night. And there were some interesting interference effects originally on these the glass on these outer things, but it had some weird colors happening. But our director at the time, Wayne Knox, didn't like them, so we got rid of that. I thought it would have been cool to quiz people about it when they visit. So I sliced some things out of this, but I will tell you a few things just about the history of it, because I think at this point, just telling you that it's an optics graduate program, you don't need a whole lot of details at this point. We cover all the same sort of areas that you've been hearing about from other programs. It was founded, as I say, at the instigation of George Eastman, the founder of Kodak. So we had historically Kodak and Xerox and Bausch & Lomb in the Rochester area. And these people wanted there to be lots of optics people for their workforces, so they funded an optics program. And we were founded the same year the stock market crashed. So we've always been associated with a good job opportunity when other things are not going so well. So yeah, I noticed in my slides, this is from a talk that other folks in my department have given to grads. So I notice we have Leica up there too, but that's because Jim Wyant, I guess, has U of R roots as well as, of course, deep Arizona roots at this point. So it's people often like to tell us that, well, aren't you from that place where Kodak went and died? And the corollary to that is that the white-collar optics workforce in Rochester is just as large as it was before. Those people didn't leave. Kodak spun off a lot of its technologies into spin-offs, and a lot of the other people who were laid off from Kodak have found jobs at mid and small-level companies that have sprung up in the area. So actually, Rochester, as a place to live and do optics, is exactly where it was in its heyday when Kodak was employing 60,000 employees. And there are a lot of other companies still around as well. But we usually like to point that out to people. Yes, Kodak has shrunk enormously, and it itself is a shell of its former research entity for PH-level optics people. But that does not mean that the Rochester area has changed at all. We have deep ties. The Optical Society of America, which is now the Optical Society, was founded in Rochester. So there's been a historical link that a lot of people serve on that. And so yeah, some books written by some of our current faculty are like every other department, have wide distribution and readership. And especially, I think, people come to Rochester and are very afraid of Bob Boyd, because you're like, that guy wrote the book on nonlinear optics. I'm terrified. But he still teaches the class. So if you come there, take a class from him. He's a trip. So basically, you can read down this list while I'm mumbling for a little while here. But like any good rich optics program, we have a wide variety of people doing a wide variety of things. I'm confident that if you came to Rochester just as anywhere else, you would find someone doing the kind of area you're interested in. We very much position ourselves as being 50-50 split between sort of optical physics and optical engineering / applied optics. In fact, all three of those really are represented about equally in our department. We have a lot of people between us and physics who are very much in the quantum optics realm and definitely don't see themselves as engineers. We have other people working on heads-up displays and optical systems who totally only see themselves as optical engineers. So it's spread out very much 50-50 there. Without naming anything particular, this is sort of a scatter shot of our primary faculty. It's in this sort of 17 zone. But you can fill that in with other people who are on the teaching faculty and people who work at the laser lab, which I'll tell you about in a second, people who work in the physics department, the MECI department, and so on. So we have a whole, this is more like the number of people that you would be able to have as your PhD advisor, if you want to think about it that way. And I saved Jaime for last just because he's the most recent join of our faculty, and he works on photonic circuits and the AIM Photonics Center that was shown when you showed that. I think there was a picture of Joe Biden talking. It was mentioned earlier today, and that effort has a headquarters in Rochester. So that's something that's going to be a big part of Rochester's and the upstate New York area for years to come. We have a couple of centers. I thought that was something I should tell you about, even though, because they're just, every place has their own. There's a lot of coherence. Emil Wolf, being a University of Rochester person, we've always had a lot of stuff going on at Rochester on coherence. So we have a sort of a center for that. The faces sort of tell you how many people are involved in that. Freeform optics, we have an NSF-funded center that Janique Roland, who spent time here, and also Creole, she's done all three. She's on our faculty, and she got this Center for Freeform Optics rolling. The Center for Visual Science at U of R is very, very strong. They're the first people who used adaptive optics, adapted from astronomy to see individual cone cells in the eye. it's a fascinating story about how the fluctuations on the surface of the eye are too great to allow you to achieve diffraction-limited imaging of the retina. They figured out how to do that, and they've just gone to town with that over the past 20 years. It's an amazing place. And we have an undergraduate center for optical design and engineering. Graduate students use it as well, but it's actually funded towards getting undergraduates with chance to use high-tech equipment. We have the laboratory for laser energetics. This is another place that was founded on the premise of trying to achieve inertial fusion. I just wanted you to know not so much about what that science project is about, although that does provide a lot of its funding, of course. But a lot of scientists work there. There are a lot of laser projects and optics projects that go on there, a lot of stuff with liquid crystals, flakes, things like that. And a lot of stuff with mirror coating, of course, because you've got to do all this stuff for this UV laser system there. And a lot of our students end up spending a lot of their time over at the laser lab. So that's an integral part. Not too hard to get there. It's a short shuttle or walk or bike ride, depending on the time of year. All right. Tells me something. We have an industrial associates program very similar to the ones you've been hearing about. These people come twice a year to Rochester to recruit and to have a day of talks and a day of interviews. We currently are at 36 of those people. And yeah, it's exactly what Laura was saying earlier, that it is totally a place where people build up relationships with interviewers over the years, and people walk into jobs at the end. And it's also true that we're seeing increasing participation from the Silicon Valley sort of companies. We have had a lot of our students going to Oculus and Apple and those sorts of companies recently. And that's a party for the whole department, and everyone benefits from that. Even if you're not trying to get a job right away, we encourage our students to take those interviews early in their careers as grad students, because you build up that relationship. It's not expected necessarily you're going to do something right away. I'll tell you a little bit about our master's and PhD programs. I'll be here at everything that we're doing through Sunday, so come and talk to me. But let's see. I did want to point out that we also have one master's flavor is one where you do one semester at Rochester, then you go work for a calendar year, January through December, and you're employed at that company and includes the summer. And then you come back, having been informed by what you now want to take classes in, you finish one more semester at Rochester and take one more semester of classes. So that's becoming an increasingly popular option that people may want to do. But we have people doing straight coursework where they get out in 9 months. We have others where they spend 2 years and are doing thesis. And the PhD program, I'm just going to put all of it on the screen because other people gave presentations. There's nothing magical to tell you there that you haven't seen others. You take our average time to graduation is also about 5.5 now. And you definitely come to Rochester, and there's no assumption of what you're going to do in that first year. We mostly get people coming from physics programs who mostly think they're going to do quantum and mostly end up doing optical engineering. So you get people to go through all that. But the first year is your free year to explore. And when the faculty give talks, and you get a chance to get to know everything. And our mix, I'm going to also, I don't think you want to read that on the time skill list, but I'll let you if you want. About a quarter of our people go into academia. We've broken out national labs as a separate thing, and about half go into what we classically call industry in terms of what our recent PhD students have done. Just my last slide on this talk is just to say this is also a place that I see I did not go to a graduate program, in my case in physics, where I felt like not as much camaraderie as I see the incredible amount of camaraderie that the optics graduate students in this department have. They are very close. Going through that first year prelim examination experience of studying that summer is an intense bonding experience. We have a weekly donuts thing that the graduate students run, and that's like a weekly highlight. But they just pull for each other a lot. A lot of them are roommates with each other, do a lot of stuff in the Rochester area. So I can tell you more about that as well. But it's a very friendly place. The students really enjoy the place, and I think they really do regard it as a home that they are very loyal to when they go out into the world, and that they also have been able to draw on those connections of our loyal alumni when they go out and apply for jobs. So it's a place that really does feel like a family. Okay, so hold on any questions you got about that while I toggle to my other thing I was going to talk to you about. And we'll see how much of this we have time for. So I also wanted to contribute to this a little bit about talking about some education stuff. I'm really into education, and one thing I really want to get out of coming here is to pair up with other people who are doing optics education stuff and see what sort of networks already exist and see how I can participate in them and see whether new ideas gel. It's when you teach in an optics department, you have the ability to teach optics classes every semester, and you don't have to have just one semester of upper-level optics. So we're more parceled out than in departments of physics, where you probably just have one semester of upper-level optics. I teach an electromagnetic theory class for juniors, and I just wanted to talk to you a little bit about some things I've done in that class, and I will see how that goes. So I'm not an expert on this, but I have a fair amount of background in some of this education stuff. And let me make sure everyone's on the same page. How many people have at least participated in something, either as a teacher or a student, that they would, by your definition, call a flipped classroom? All right, so, right, a lot of you. So for those who aren't raising their hands there, the point of a class, if you're designing a class as a faculty member or if you're a student taking it, you're going to get exposed to some stuff, and then you're going to be learning how to use that stuff, right? That's your typical upper-level science class. And you've got both in and out of class time to work on that, and the typical model is something like this, right? Classroom time, I'm teaching people about Fresnel reflection and refraction. I'm teaching about the origins of refractive index. I'm talking about dipole radiation. A lot of heavy mathematical derivation stuff that underpins it. And so this is the typical way that you do that, by presenting a lot of that derivation in there, and then the homework is where you work on applying those things for the most part. And the idea of the flipped classroom is that you may do a lot more of that. So I want to talk to you a little bit about my experiences in a class that you might not think you could flip, because how can you not present all of those derivations in the classroom? That's sort of the essence of what it means to master this material. So yeah, electromagnetic theory. I'm throwing up a slide here from an NSF project that I was on interviewing students. But I throw it up here so you can get a sense of, I care in this class both about the students having strong conceptual models of what they're thinking of when they think about the idea, say, of a plane wave, which is a very complicated concept, right? X, Y, and Z, and it's moving in space, and it's moving in time. But I also want to make sure they walk out of there being able to look at some expression like this and also be able to utilize that to talk knowledgeably about plane waves. So I'm curious about making those connections. And here are the postulates I operated on in terms of trying to flip this classroom. So I can't get rid of the derivations. That's postulate number one. My second postulate, which is pretty well established by education research, is that you don't internalize a lot about mathematical derivation when you're seeing it for the first time. Doesn't matter the format. You have to have some time to reflect on it. That's not happening when it's being presented to you for the first time. I experienced this, and I think most of the teachers would agree. Caveat to that, if I make a mistake, someone will raise their hand and ask if I missed the minus sign. But if you do it flawlessly in terms of technical content, you don't tend to get a lot of interruptions during the derivation itself. That's an important postulate. This is one that I believe. I can't really prove it to you, but I believe that because of course there's always been books, right? You can always tell people, read the chapter, I'm not going to do this derivation, it's in your book. I think we know that would not result in a lot of students reading the derivation in the book. If you were to teach your class assuming that, it's probably not going to go very well. I do believe there's a chance that people will, of their own volition, watch a video, but I'll defend that. This is the most controversial one. It's not one I believed when I started off. I now strongly believe that fifth postulate, or I wouldn't have called it a postulate. So we'll come back to that. In the interest of time, because I talked a little bit more about Rochester than I thought I might, I don't know exactly when I'll stop, but let me just, well, I have to at least show you, I guess, the basic idea of one of these tutorials. I'm not going to try to play the audio, but you can imagine me talking. If you've ever watched a video on Khan Academy, it's the same sort of thing. In my case, these videos are mostly just me talking and writing. I sometimes bring in a demo, like a MATLAB simulation or something. But what you'll be getting in something like this is, okay, yeah. I'm not running this the way you would see it as a YouTube video. I got it away from the internet, so I wouldn't have to rely on it. But you can see I'm just sort of sketching out something. I would be talking. And in this case, I'm talking about how a wave plate affects the polarization of light. And so I'm sketching out something of that sort. I also I wanted to show you one that's a little more mathematical. And it's probably going to start trying to play over here, so I'm going to shut it up. So this is one where I'm trying to derive the initial steps of the vector potential of an oscillating electric dipole. And what I'm trying to emphasize to them here, here's an electrostatics problem on the left, electrodynamics on the right. And you can see I'm setting up some very parallel situations. And again, I'm talking all the way through, and you can sort of see how that's setting up there, right? So that's the sort of thing that you should have in your mind when I say that I've made my students watch a video. OK. Here are some objections that you have. It's so lazy to record yourself doing a video, doing a lecture, and then put it online. That's just lazy. It's like, why don't you actually teach the class? Students can't ask me anything while they're watching this because I'm not there. It's asynchronous. And even if I believe that it's authentic, and even if the education community thought that it was authentic to do this, maybe the students will not like it. Maybe they will think that I'm being lazy. A few technical details, just in case you haven't recorded these things. I had to go through a learning process here. The tools are not, the middle column is sort of antiquated, but when I recorded these things, I do think having the freehand writing is actually important, personally. I think it just makes it move at the right speed, as opposed to PowerPoint, like popping everything up. But when you do your freehand writing, that one's pretty easy. I now have a Surface. I don't think I would use this external tablet next time. But this is what the guy at Khan Academy used. Any drawing program works too. You see the name of the one that I happen to use. But what's important, I think, being able to quickly change between pen colors and pen functions is actually pretty useful, because then you can move more smoothly through your presentation without wasting time to go off screen to switch the color. Lots of screen recording programs out there. I can tell you about the one I happen to use. One thing I like about that not all of them use, I was originally using the software that U of R was providing, which is Panopto, like capturing a screencast. Two things it didn't allow me to do. One was I couldn't capture just a part of the screen. It's really nice to be able to just see part of the screen, have other stuff off to the side, and you drag it in when you want it. That was annoying. So look for something that allows you to select a region of your screen to screencast. It's also nice if it has a little ball, like you saw that I have, a yellow Tinkerbell ball that was moving around. It lets you follow what's going on. It's as if you see something moving. It seems to keep their attention. And I disseminate it by converting these to YouTube videos, and it really is nice to have them play back at higher speed. That allows me to talk slower, more methodically when I'm recording, and still allows them to watch it at sped up speeds. And they don't really lose anything, because I'm talking pretty quietly. All right, so I wanted to mostly leave you from this talk with a few guidelines, lessons I've learned from doing this. This is not rocket science to flip your class, of course. From everyone from Khan Academy on, although it was originally just because of file sizes for Sal Khan, education research has sort of suggested 15 minutes is sort of a max. If you're watching it at sped up speeds, OK, you can record a half-hour video. But don't make it longer than about 15 minutes. Break it up into modules. You're going to thank yourself next year when you decide to keep only half, get rid of one part of the talk. Then you can move that part around without having to edit a lot. It's nice if you can record the video as a single board without any erasures, because then in your class, you can put that board up and say, did you have any questions? Now it's time for questions about what you saw. I don't do that beginning of the class, but at some point I'll say, the juices are flowing. Any questions about the video, about the tutorial? And it's all there, right? It reminds them, oh, yeah, that's what I saw. I definitely found that it's important not to just try to run it dry. Like, I basically sketch out the entire thing ahead of time and then do it again while I'm narrating it. If I didn't do that, I found that it just failed. We all often wing our lectures that way. Everyone's given some lecture, if you've ever given a lecture, where you didn't know exactly how you were going to use the board. And it more or less works out. When you're committing it to this sort of goal, I found I was never satisfied with my board usage unless I actually practiced it ahead of time. I wish I could do that before every talk I ever give, but it was good to do it there. I really think multiple colors are a way to get a lot of information onto one board without overwhelming the visual field. One color alone, you have to be a lot less dense. You don't get as much in. The biggest thing of all, though, is remember that I don't think that you can make good recordings unless you have editing software. If you just capture what you were doing in live mode, now it's just a lecture. Now it's no better or worse than what I probably would have done in class. It's the ability to edit it that makes it, in my opinion, the fifth postulate. You can do better than you would in the classroom. Because all the times when you're a little bit tongue-tied, the time when you make a mistake, it's gone. You can't make a mistake if you allow yourself the time to edit. It obviously means you have to work harder, but I found that really worth it. So make sure if you do this, that you've got some sort of software that doesn't just capture you speaking. There's an analogy, right, that when they started doing TV broadcasts of theater, they would literally just go into the theater and show someone acting on a stage. And only later did they figure out how to make drama for the film or for the TV. It's a different medium. And so don't just record yourself doing what you would have done in the class in real time and say, that's my offering. You can also make the lecture about half as long, by the way, if you edit it well. This thing about being silent while writing long math expressions, that's really boring during a chalk talk, right? Okay, I've got to write out this long integral over here. What I learned recording my videos is as long as I shut up while I'm writing it, then when I'm editing, I can just chop that section out, and then it will just pop up there. So there are certain places where it's good. It actually is faster than doing it in front of the students. And speaking slowly allows you to play it back at increased speeds. I'll skip that. So now this is the benefit I get from using this. Lots of people come into class and give the students an initial sort of challenge question, but the fact that the students, they watch the videos and they fill out a quiz online, which I skipped over, but they fill out a little quiz about it. And so I have that information, and I make my entrance challenge based on that. I wasn't able to do that before when I was not making assumptions on what the students had done before coming to class. I'd have to base it on what had happened last class. That's not as fresh in their minds. I really like this one, that when the students give me feedback on questions, someone mentioned writing across the curriculum. I like the ability, don't read this per se, but I'll ask them a question. Okay, this is actually about that dipole one that I showed. Why was I making this comparison between these two different situations if I only care about the one on the right? And students will give a bunch of questions. What we did a few times in the semester was I let the students rank or just vote for which ones of the answers they thought were the highest quality. And it was a way for me to comment on that and give them feedback on what I thought a high-quality answer was. And that comes back on the tests when I give them some short questions to answer, and I've sort of been able to convey to them what I think a good quality answer is. And as I said, you can show the screenshot of the final board of the lecture and ask them, at this point, do you remember anything you'd like to ask? The main thing is that we can then spend time doing what you're supposed to do in a flipped class, which is work on the homework problems. Like I'm literally giving them the homework problems and helping them through them and letting them work. That's the point of what you do. So there are some advantages. I'm just going to skip over the advantages thing in the interest of time. Okay, so the students watch the videos, right? That's what you're wondering. So the first answer is the first year I did this, I was able at least to see how many YouTube hits there were after I released it. I'm not very sophisticated about checking whether they're watching their YouTube videos. But then you'd say, okay, but that doesn't prove anything, right? That just says whether they clicked on them. Do they actually watch the videos? Well, they were I embedded the video link in a quiz they were taking on Blackboard, and most people filled out the quiz. So I figure if you lead the horse that close to the water, I can't actually make them click on the link to the video. They're laughing because they maybe did this once. But at least I thought if you're that close to a link that you're going to have to watch for 10 minutes and it's a video, most people are just going to click on it and say, okay, fine, I'll watch the video. So for the most part, I think so. All right, so you're still wondering, are they paying attention when they're watching that video? They're in their dorm room, but this is the standard physics education response to that question, right? And when you give a lecture in class and it's over, it's gone, right? They can't pause me. They can't interrupt me in class. But actually in the video, each person on their own schedule can pause me and rewind me and speed me up, and watch me again. And so they do all of these things. Anecdotally, I know they do all these things. I hear my voice in the hallways. So the guy next door to me happened to play me a lot. So yeah, he was probably just trying to get a good grade. Anyway, and I won't make you read this, but I asked the students mid-semester, name one thing I should keep doing, one thing I should stop doing, one thing I should start doing. The keep doing thing very frequently came up saying videos, videos, videos. So I really think that there was a lot of support for the videos being a useful part of class. And what I liked was that the comments weren't just saying, I like the videos, but I like the videos and the discussion in class. I like when you go over the video questions in class. So people were seeing that the videos were not unrelated to the class experience. All right, I'll close with some pitfalls. You have to emphasize to students that if you're going to put video content online, it's a lecture. They should have their notebook out. I found in class sometimes people didn't have a set of notes to work from, so when I would let them work on their homework questions, they would be calling up the videos. That's not what you have to do it yourself. You have to write down things you think are important during any sort of lecture. It didn't happen this year, but the previous year people said, you're double lecturing us, man. You know, you're giving us these things, and in class, if it's a technical topic, you're giving us more lecture. So I have to really discipline myself to keep my end of the bargain and not lecture in class. You do have to respond to things when they come up in class, but you try to not have primary lecture material happen in class unless it's not something that could fit into the videos. The biggest problem with this stuff is that they are time-consuming to record, so when you do the class next year, it's tempting to just keep them the way they are. I usually re-record or add a few each year, but the first year I made like 40, and it took a lot of time, and you don't want to do that every year. So there is some inertia associated with it. And lastly, when you put a lot of your content online like this, more students skip class, and you will have some students who are able to get B pluses or higher in your class without often coming to class. It's just a few, but you just have to accept the fact that if that gets them through it and they can pass your tests, is that a bad thing? I don't know. They're watching. A lot of students who don't come to class very often, I can see that in a semester, watched all the videos. So, but it is something you have to get over, thinking like, I am the reason why they're passing this class. My live voice is getting the, no, of course not. We all know that's not true, but you have to really face up to it when you teach it this way. All right, so I really do believe this fifth one, this is my last slide, I've really come to believe that if I polish and edit and condense what I wanted to say in class live, I can't think of any aspect of what I'm doing that isn't better putting it online for them to watch there. It's a better tool for them. It's a better resource for them. I'm focused more on what I want to get out of it. And it doesn't evaporate after I say it once. Oh, and if a student misses class, they can still catch up to it. You know? So there's a lot of advantages to it. You may not agree with all the postulates, but I wanted to let you know what my thought process was on that. And with that, thank you. And so I'll rip this right out now, but while we're switching over. Yeah?
I've heard a lot of competing theories on this, and actually my advisor does a lot of this. What is, I guess, the comparative advantage to watching your videos over just strictly reading the book?
Well, I guess one thing I think is that, you know, the reason why people are taking this class rather than the reason why people are in college taking this class in principle rather than just reading the book is that there's an added value to what the professor's own insight is into what the book is talking about. So that's what I would say, is that we have to retain the belief that in the video, the comments I'm choosing to make are the things that I would have said in class. I lived with that.
I guess my question is more like a lot of people who do this just regurgitate the book. I guess that's what I was trying to.
Right, you certainly should not be regurgitating. Yeah. You certainly, I mean, that's a softball, I suppose, to treat it that way. But yeah, of course, you're not regurgitating the book. Yeah, you're trying to say whatever you think is most important. And, yeah.
How long did it take you to do all the recordings?
I was worried someone was going to ask my wife. I got a little anal about it. I started going like, how much can I shave off? So it was the editing software that was the limiting factor for me. I think with good editing software, it was easy to stop and start. Probably, I feel like it took me about maybe 2 hours from sitting down to when I was done recording, planning to end of recording. Maybe another 1.5 hours, and that's to make a 15-minute video. So it was something like 3 to 4 hours for a 15-minute chunk. So it's you would never do it if you weren't going to. I've been teaching the same class at U of R for like 15 years, so I knew I would get to teach it for a few more years at least. You have to know that you're going to teach it more. It's not worth it for 1 year, of course not. No way.
One more question over there.
Yeah.
So
You talked a lot about how lectures were better delivered in recorded form. How about problems? Are they more beneficial when done in class as opposed to outside class?
Right, so the question is whether problems are more beneficial when they're done in class. My core belief, and it's not an original belief, is that the highest added value I can provide, that the professor can provide, is to react to things that students are actually having problems with. So using class time to deliver something pristine that no one interrupts about seems like the worst possible use of that precious time that I have. I sort of believe that I have no control over what you do when you're not in my classroom. So when you're in my classroom, I want at least some of you to run into problems so I can be, as they say, the guide on the side and react to, okay, I'm seeing several people are having this problem. Okay, let me jump up here and make a quick comment. So the sage on the stage stuff seems just miss the point of leveraging. You know, I'm not an expert at making greater lectures than what you can find online, but I am a local person who can actually answer your question because I'm live and I have expertise. So I think it's good to have students solving problems in class. Yeah.
Okay, just one more question. We are running out of time.
I'm putting on the backpack. Yeah.
If you problem solve in class, do you think there's any risk of the students maybe not getting the same kind of painful but really educational experience of having to fight their way through a problem?
That's fair. I mean, when you make this deal with the students, you have to tell them that some of the problem sets are now the things they're doing in class. Because, I mean, I guess the problem set is actually being worked on in class. Literally something they're going to turn in. No, I think not. I mean, like most people in engineering, I treat my problem sets as basically low stakes warm-ups for the exams. And there's plenty of pain on the exams, right?
All right, let's thank Andrew. Tell us about digital protein microarrays.
Thank you very much. Thank you for inviting me to this winter workshop. It exceeded all my expectations so far, and I've been here only just today. It's a great venue, and also the line of speakers that we have so far. It's a high bar. I'm pretty loud in general, but...
We're recording when you can
Oh, I see. So do I repeat it? Is this on? Hello? On? Yes, it's on. Okay, good. So, I'll talk about optical interference again. Right? It's going to be at a very different level than what you heard this morning. So what's in the talk for you? Since most of the audience are students, first I'll talk about technology and how I think it will impact life sciences. This is personal views in general. And also I'll talk about how multidisciplinary nature of the research is in optical biosensors. And that will be exemplified by the type of people that work in my lab and people we collaborate with. And also I'll show you that fundamental principles that are known for a long time can be applied to engineering solutions. Simple is better. More complex isn't necessarily a better solution. It could get you better publications, maybe. But at the end of the day, what works is usually the simpler approaches. And also, there are so many problems that you can pick whatever. So you should pick the problems that you want to work on and what you can solve, because there is a whole range of things. Don't focus on the problem, focus on your own capabilities. You'll find the problem to solve. And there are new and important applications of the old stuff, and that will be exemplified in my presentation. Perseverance is very important as a young researcher. Follow your dream, persist, and it will pay off. And undergraduate research can be of consequence. And I think my presentation will deliver that message loud and clear. Okay, what is my motivation in what I'm doing? Enjoy curiosity-driven research to make the world a better place for all of us, and training, transforming students. Before Simpsons, Matt Groening had Life in Hell, and that was part of the cartoon series, was School is Hell. And you can't read this little one, but it says basically, oh, come on, people are outside having fun, drinking beer, so on and so forth, having a picnic. And the other bunny, who looks a little worried, says, well, I'll be out in about 5 years. That's a PhD student. And this I like very much. This came out in '87. That's like second or first year of my master's degree. And it says, will your research make the world a better place? And yeah, sure. I put that next to my my own rendition of Simpsons character that represents younger me with red beard and red hair. I don't have a red beard. I don't have hair. So that took care of that time. Right, so you can look at another motivation. This is in vitro diagnostics market, molecular sensing for medical applications. That is growing twice as fast as the pharma market. And it's a $60 billion market worldwide, and it will grow to be $100 billion in no time. And there is also a cynical perspective as a faculty member. This is a Dilbert cartoon, the more modern era. This is, again, at least 15 years old. The boss is looking for a 6 years project to boost my career, and there was mention of what funding agencies, is there freedom? Tom was pointing that out. Is there freedom? If you're submitting proposals, you have to sell your research, and what government funds defines which way the research is going to go. Is this really academic freedom? Within that constraint, we can actually have some freedom. But the cynical person is like, it only has to sound good and not fail until I get a better job. So, and then, we want something in nanotechnology, stem cell for fighting terrorists. All the buzzwords, all the omics you can add, whatever. And so on and so forth. Okay, so a more altruistic motivation, which is a clear violation of causality, because you can come up with these motivations after you've actually done the work, as opposed to before you start the research program. The research I'm going to talk about actually started in about 10 years ago, but 5 years ago we took a bunch of students from our undergraduate programs in engineering to Nicaragua to give them a taste of healthcare delivery in the third world. So this baby I'm holding in my arms lives in a shantytown built on a city dump, and they share a spigot of water outlet with 3 other families, and her family has water only after 10 p.m. until like 2 a.m. And that's the private lab for molecular testing across from the city hospital, which doesn't have this capability, so people have to pay extra money to get their blood tested in this facility. So there was one PCR machine, polymerase chain reaction machine for dengue virus detection, infection detection, and you had to have your blood transported in a cold chain from point A to point B, and you get the results in a week, maybe, if you had the resources. So the basic idea is, can we have the best technology that it doesn't necessarily require the richest nation's resources? So if you look at diagnostics and biodetection in general, the most common method is ELISAs, enzyme-linked immunosorbent assay. It doesn't have to be enzyme. Now the fluorescent tags are very commonly used. It's basically a capture molecule, and you capture the target, which is insufficient transduction of signal, so you decorate that with a secondary antibody that provides more specificity and a more observable transduction, and which has an enzyme or fluorescence attached to it, then it can be seen. Label-free sensing has been the holy grail. Without needing the secondary tag, can I see the interaction of the first target molecule? And Biacore commercialized surface plasma and resonance technology. And GE Healthcare bought them for almost $400 million 10 years ago. And this is still an unproven technology for its impact in healthcare, but it does work for research and development. For infectious diseases, PCR is the most sensitive technique. It can be a compact instrument, but it requires a lot of sample prep. So my colleagues in the medical field tell me that if you wanted to use PCR in Africa, you have to first ship a truckload of equipment and set up a lab. Then you can do PCR, which is not necessarily desirable. Optics can provide interesting solutions, and I think you heard resonator sensing yesterday. And the idea of the ability to detect single particles can be not only very sexy, also very, very useful. So one of the things, as I mentioned, that you have to be opportunistic. I'm at Boston University. We have a photonics center, not nearly as old as the Rochester or Arizona, but it started in about 20 years ago. 97 is when we had the building completed. And we have a very strong presence in life science and engineering. And there is also the National Emerging Infectious Diseases Laboratory, unfortunately named as NEEDLE. And it's not yet certified to operate in BSL biosafety level 4 facility, but it is an important emphasis area for our university. So in this environment, I got to make apple pie. So what I'm going to talk about is our technology, interferometric reflectance imaging sensor. This is after we called it spectral reflectance imaging biosensor. And Italian collaborators told us that they cannot say CIRIB. You have to come up with a better name. So I had a competition among my students, and this is a winning acronym by a student who wasn't working on this. Anyway, so it does allow you to do biomass measurements, and you can use higher magnification optics, and on the same spots, you could also count single nanoparticles, individual nanoparticles. So why analog versus digital is important? This is stolen from David Walt, who is founder of Lumina. And his new company, Quanterix, is working on digital detection. So the readout of an analog signal requires a precision which limits its sensitivity. So you have to make a distinction between two different levels of signal, and that defines how sensitive your measurement is. Instead, if you're making a digital readout, you're making a decision between presence and not presence, 0 and 1. And that decision can be made with higher precision for each individual event. Then you have a collection of events, you can have higher sensitivity. Those of you, the professors in the audience, might have seen these turntables. So the information was coded on vinyl recordings as an analog information. So your stylus had to follow dips and troughs and valleys and peaks to reconstruct the recorded information as an electrical signal by the precision of the stylus. And if you didn't have a very good record player, the rest of your music system doesn't matter because you have noise in the system. Now, some people like that. Now there's a bunch of retro people who wants to actually have this noise of the record player, and today they can be artificially added on top of the digital sound if you really desire to have this hissing. In 1983, Sony came up with the compact disc player, and we never looked back since then. At the time, it was an instrument which was $900 in 1983 dollars. It's very expensive, but quickly we've discovered that this instrument doesn't have to be very, very high quality. And digital reading is actually much simpler, and the fidelity of the instrument, it doesn't have to be very high. And you can do a lot of error correction. So digitally encoded. It's not like analog signal directly read out. This is digital information that can be at much higher speeds, and you can do a bunch of error correction to get rid of. Well, I shouldn't be talking about error correction when Masood is sitting here, or optical recording for that matter. So a Simoa analyzer built by Quanterix does actually 230,000, if I'm not wrong, digital protein readouts on truncated fiber tips in microwells. So what happens if I can have a vinyl player in a car? It doesn't work very well. I have seen once in my lifetime a vinyl player in a car when I was a kid. That didn't work well, I remember. But if you are Muhammad Ali, if you have all the money and the strength in the world, you can make it work. But now you can, 25, 30 years ago, you could run with music because you could carry it with you. It was immune to vibrations, and the fidelity of the readout wasn't as important. So when we can read things digitally, make ones and zero decisions, it can be much better. So now, how do we do that? Optical interference is the working principles of our work. And it can be best understood by looking at a soap bubble. Light reflects from the top and the bottom surface, interferes, and therefore you see colors at different points depending on the soap film thickness and wavelength of the light. So what most people don't realize, I mean, you've all seen oil slicks and soap bubbles. The thickness measurement you're doing by deciding the color of a specific point is about 10 nanometer accuracy. For women, it's probably better because they know that the colors are only green, blue, red. Like there's other colors like forest green versus jade green, something like that. Because when I tell my wife that's green, that's like, that's not green. That's some shade of blue of some sort. So if you can make a better precision the definition of the color, you have a better sensitivity measurement. We heard the Leica Talk today. This is a slide I had in my slide deck for many, many years, and I took it out just before September 2015. I've given up on LIGO, and I was proven wrong. I put it back in, only after like a month or two after taking it out. So that is a much higher precision measurement. We don't have to do this for biosensing. We can do a little better than this by using instruments as opposed to just an eye. When you look at this technology, you've heard of Newton rings. The idea of interference was identified by Newton. And Airy had formulated it. In this article is 1830-something. And he had to use terminology which is kind of foreign to us, like let the vibration in plane of reflection. So, there's no electromagnetic theory, and still he's able to come up with the exact same equations for interference as we use today. So what is a great soap bubble? Best soap bubble you can get is oxidized silicon wafer. This is like the purest material you can have because there is trillions of dollars of semiconductor industry all relying on having a good oxide on silicon. And the primary reason, from my perspective, silicon is a wonderful material, it's an elemental semiconductor, and it has a very stable oxide, so you can have an insulating layer in a semiconductor system. And when you oxidize silicon, you form a thin film, which can be controlled very, very precisely. If you look at it at different angles, you see different colors. Or if you etch it down to different thicknesses, you can generate different colors reflected strongly. Actually, in the old days of silicon fabrication, engineers would look at the color of the film to decide how thick the oxide is. So we can take this, and instead of measuring the color at every point, you can shine light at different colors and take the entire sensor surface's image, and for a particular point, you'll end up with a reflectivity curve. And if there is anything put on that top of that film, it will have a shifted reflectivity curve. And the shift is proportional to how much material you have. That is the basic principle behind interferometric sensing. And you can do that, as I was corrected by my signal processing colleagues. You don't have to do all these 20 measurements. You can actually do 3 or 4 measurements to fit a well-prescribed reflectivity signature. Now we know that we can actually monitor a single point once we establish the thickness in a narrow range. So this is the methodology we use for biosensing. Now, going back to my point of perseverance, when I started to work on this, it was with David Bernstein, one of my PhD students. And he insisted that he wants to work on biosensors, and we had no money. We had no lab. So we borrowed space in somebody else's lab, and we put together bits of pieces of money from here and there. He worked as a TA. We started working on it. And soon enough, in a few years, he has established that we can do this in using a tunable laser. That was a bad mistake. We could use a 1,000 spot array, and he commercialized. He started a company called Zoeray. That company has failed so far, and we've shut it down. But the basic ideas behind it still survives. And we were able to show with Zoeray that we can do dynamic measurement of protein binding on a multiplex chip. We were actually trying to reproduce these results today. This is in 2008, 9 years ago, because with our new findings, we think we can make it more applicable, more commercially viable. And a couple of students who worked on that project are now working for Illumina. And he's working for a startup doing cell sorting. Now, completely something very different. How many of you have seen Monty Python? Oh, good. Thank you. We're in the right crowd. Now, using the same chip, can we do something very different? It's a soap bubble with a thin film of oxide on silicon. Can I see viruses, or can I label proteins or DNA molecules with small nanoparticles that I choose? Can I see them individually and count them? Optical microscopy is known for about 400 years. And obviously, once you have a way of looking at the microscopic world, you look at a variety of different things. Like, you all looked at onion skin and some blood samples. And people discovered that there are cells. And these are actually drawings. Hooke published a book which had lots of drawings, because there was no way of recording the images they see. So you would look and describe to someone who is drawing, and they will draw the pictures. When taking photographs using microscopes became reality, it truly became seeing is believing. So you could take pictures of microscopic objects. So as soon as they put together a couple of lenses and achieved magnification, they were able to see these cells. But 400 years later, we still struggle seeing things like viruses because they are small. And wavelength of light in the visible domain is large compared to the size of these particles. So wavelength of light is around 500 nanometers. Viruses can be as small as 20 nanometers. So what happens when you have small particles? This is a bacterium. I can see this under an optical microscope. These are 80 nanometer gold dots. This is for a surface-enhanced Raman scattering experiment, you can see the size of those with respect to the size of the bacterium. The problem is the contrast in regular conventional microscopy is intensity contrast, and it's based on scattering when you have small objects. And the scattering scales with the volume of the particle. And you observe intensity in the far field that you take the square of this, you end up with r to the 6 dependence. What that means is that if an object is 10 times smaller, it is 1,000,000 times less visible. So typically, when you try to see things like viruses, and they have small refractive indices also, they blend in the background, they cannot be seen. We put the soap bubble underneath. Now we do interference. We do a homodyne detection, basically, where the incident light reflects from the reference surface and interferes with the scattered light. So you focus on this term. You can adjust this sine theta by controlling the focal point and the thickness of the silicon dioxide and make this strong. And that depends on the third power of the size. So instead of dropping by a factor of 1,000,000, you only drop by a factor of 1,000, or you're 1,000 times brighter. So all of a sudden, these nanoparticles that are not visible will come to life. You should be able to see them. This is not how that research started. It started that I'm teaching electronics. That's me in, I think, 2008 or so. And one of the students in this particular classroom was George. And the other one was Rahul. They knew nothing about optics. I gave them a book, right? They wanted to do their senior design project with me because they like me as a professor, and this is where professors recruit their best students for research. And they wanted to do their senior design project. I said, okay, but my lab works on optical systems. Do you know much about optics? They said, zero, nothing. Said, okay, well, over the summer, study this book. Just the first 5 chapters or so. They did. And they came back, they said, okay, they're convinced that they can work on this. And I said, all right, so I have a new project for you. I want to apply our technology to nanoparticle detection. Because I did a back-of-the-envelope calculation. If I'm doing a thickness measurement, which is a picometer capability, not atometer or femtometer, just a picometer, using a very simple soap bubble like silicon wafer. If I have a virus, if I get my optical magnification good enough to have a 1 micron resolution, which is trivial for visible optics, that 100 nanometer virus spread will provide me about a nanometer signal. So without any scattering model or anything like that, it's just the back of the envelope. Let's say this should be visible. And people didn't believe me. I said, okay, let's assign this to a couple of undergraduate students. And they did it, and they won the Best Senior Design Award with this data, which is this picture, right? They had 2 particles. They were fluorescent labeled. They were identifying them in the fluorescence image. And they looked at the surface profile. And this was a signal about 1 nanometer in height. They said, aha, we can see them. So this is the image they were able to get at the end of the summer after they graduated. This is fluorescent labeled 100 nanometer virus size polystyrene beads. And that single particle detection became simple particle detection. And the signal you get from these particles is much more uniform than you would get from fluorescence labeling. Although manufacturer of these dots would tell you that they're uniformly labeled, we claim otherwise. So the way the system works is, for detection, you have a functionalized surface with different capture molecules. And in this particular case, these are exosomes that we're detecting. These are exosomes are small vesicles secreted from cells that are known to communicate between cells by passing molecules to each other. So the scattering is interfering with this, and you can see it. And not only you can see it, it also relates to the size of the particle. So you can also determine the size of the particle by doing this measurement. We're not beating the diffraction limit. These particles are sparse on the surface. They're far apart from one another. Maybe there is a particle at most at each micron spacing. But they're invisible if you do not use this reflecting surface. They become visible. We typically have 1% to 20% contrast on the image, depending on different type of particles. And then you count them in a multiplex fashion because you can functionalize the surface with having spots of different antibodies on the surface. On a very simple chip, you get images like this, and you can characterize the particle size. Okay, now going back to being opportunistic and being driven by funding, and to this, right? Nanotechnology, stem cell for fighting terrorists. Our largest grant on this topic has come from a NIH biodefense program. And they were interested in hemorrhagic fever detection. Those are Ebola, Marburg, Lassa fever, for example. And these are all BSL-4 pathogens. And we do have a BSL-4 facility, which is not yet certified. So we work with UTMB, University of Texas Medical Branch in Galveston. And we are still working with them now. And so one of my successes is I have a virologist posing next to the optical system in my lab. That's great. He's the PI of this grant. So we couldn't work with these in our lab, so we used a model virus, which is modified to express the proteins of these nasty bugs. And if you can detect this modified pseudotype virus, that means you can detect those. So the basic idea is you have a tiled chip. You take a picture before incubation, after incubation, and you can filter out the wrong size particles and focus on these, and you can have a sensitive detection method. Now, we got some press during the Ebola outbreak, and recently we've shown also that we can detect viruses of different sizes. This is Zika virus. This is like the smallest thing we've detected so far. It's about 40 nanometers in size. To verify SEM pictures with our optical images and an overlay, and then you can determine the size of each population. Vaccinia has lots of dead viruses and viral pieces. That's why it has a bimodal distribution. This is actually the size of Vaccinia. Doing this in a dry chip has certain advantages. It's very important that you have a good contrast. And air is a very good contrast provider because its refractive index is as low as it can be. In solution, your contrast is not as good. So you can see the contrast drops by a factor of 3. But there are advantages of working in solution because we can capture and detect. We don't have to worry about the background images. Any new particle is a target particle. And you can take videos of it. This is a blown up image. Every bright dot is a virus. So many viruses are flowing across, and as they get captured, they become visible. In the solution, they have very little contrast because they don't have the interference term. Once they get captured, they satisfy the requirements for having a bright interference term, and we see them. And we can do a test in a closed environment without any sample prep. So this is the modality of operation right now. We have a passive cartridge. You put the sample in, close the cap. It wets the channel. And you peel off the seal, so air is let in. So this absorbing pad starts to suck the solution. It goes across. You wait for a while and count. And the sample you put in can be red blood directly from the vein, in which case we have a filter to separate out red blood cells. So the final topic is, how do I apply that to molecular detection? So it's been known for a long time that we can tag things, label them with microparticles to improve detection, and it can be in optical or electrical methods. The advantage we have is that we can see really small particles. That means I can pick very small tags and avoid any influences of having a large tag attached to a molecule in terms of the assay feasibility. In which case, instead of using a fluorescent molecule, we can use as small as 10, 20 nanometer gold nanoparticles as labels, and then we count individual molecules that we capture on the surface. So we were able to show sub-femtomolar sensitivity in serum and whole blood for protein detection. And Joe presented results on nucleic acids yesterday at the poster session. And we apply that to hepatitis, allergy chips, and we demonstrate that we can actually do as well or better than existing technologies in a very simple and inexpensive platform. And more recently, we are also developing different properties of light to aid us, and that's namely polarization. Because you can pick the label yourself. You're not limited by what nature has given you. You can put a rod as a label, in which case it is polarization sensitive. You can rotate or use circular polarization to extract a larger signal from this polarizable object and use much smaller numerical aperture and capture a wide field image. We can have a 1 millimeter square image on which we are counting single protein or nucleic acid molecules. So instrument matured from a tabletop to a first commercialization effort by David, and then we started to use LEDs, made it really small. It could be a really, really compact instrument if we need it to be. And another David from my lab commercialized it for a second time. That company is still alive and well for single particle detection, specifically for exosomes. And some of the results I showed is from on the instruments he built. So these instruments look a lot better than what's in my lab right now. But I see this is a Turkish cartoonist. The engineer is talking about inventing the wheel, and the marketing person is telling him which to market first. And I think we did fail with trying to market the triangular wheel. I think, but right now, its next gen arrays is now called NanoView. I think it's a wheel that will roll if you push hard enough. And we're not too far from actually perfecting the technology. So we can take a sample, put in nanoparticles in, directly detect and count viruses or nanoparticles, exosomes. We can also detect proteins that are converted to nanoparticles. And we've shown that you can do that on a cell phone if you need to. There's not much reason for our instrumentation to be incorporated with a cell phone. But our Associate Dean for Outreach and Diversity actually takes our technology to high school and teaches the high school kids how interference can be used to read out very small features. Students being able to see a nanometer height on a surface are very impressed. I have 5 PhD students graduating in this calendar year. That's going to be a big loss for my lab. The instruments kind of look like this in our lab right now without any shell around it. And finally, it is a big effort. So we have, this is the heyday of my lab. We had about 20-some people, and we had chemists, physicists, biomedical engineers, electrical engineers, computer engineers, mechanical engineers. I have 2 PhD students graduating in mechanical engineering this May. And we have medical doctors working together with us. And finally, I think future is bright, so we can do a lot better with microscopy. This is what I bought for my son. He wasn't shown any interest in this because he could see the little objects better without putting it under the microscope. This is a 1x. So it didn't really help. So one day I hope that I'll buy him a real microscope. I think I ran over my time. Hopefully it wasn't too boring.
Over here for the reception. Okay, great. Thanks again, Selim. So the next speaker. The next speaker is Professor Peter Smith from our own University of Arizona, and he's going to tell us about his wonderful work, The Joy of Space Exploration.
Maybe you'll help me.
Let me fit you with the microphone. Where it's going to go? Over here.
Testing. It doesn't matter. It should work.
I didn't know I was the resident computer expert.
Well, now you are.
So the brain power we have at the podium is amazing.
Yeah, it said 2017. Yeah. Let's see if it'll work. Oh, there we don't go. Need more brain power. Come on.
What was the last presentation? Was it from this computer?
No, it's from here.
I'm not lending my brain power on this crap.
Hey.
Or are you going to use it? You going to use it too?
It's not plugged in. That's the problem. So how do I advance the slides? Is there a button?
I can always do that, but I don't know whether we have it clicked.
Do that. Okay. No, that's all right.
So how many PhDs does it take to screen?
Okay, we ready? Yes. Well, my talk is about basically my life. I came here to the Optical Science Center, as it was called, in 1975. And they said, well, you're going to need a project. And I said, well, give me a project. I don't know what I want to do. I came here with a blank slate, you know. And they said, well, we have a project doing some image processing for a space mission called Pioneer 10 and 11. And they had just, a few months before, flown by Jupiter. This is the first time a spacecraft from Earth had ever gone to an outer planet. And they said, but we need somebody to help with the image processing. And there was, of course, a small team of people working on this. And that's how I started here. And I hate to say it, but I never left. What year is it? 2017? That's been 40 years I've been here, my God. And yet, there's a lot of joy in exploring space robotically. And people ask if I'd like to go myself. No, I don't want to go. I want to send robots. Just like you don't want to be infected by your viruses. We don't necessarily have to go personally to space, but we can still have a lot of fun. So my talk today is a little bit about the missions that I've been involved with, and also encouraging those of you who are beginning your careers. And I'm retired, so I'm not beginning my career, but you're beginning yours. Find a field that's just opening up. In my case, if you went to the library to look up books about the planets, there's only a few books, and they had very little information about each planet. We knew about their orbits. We had fuzzy pictures of them, and we knew maybe their mass and a few things, some spectrum. Basically, we didn't know a damn thing. Now there's entire libraries filled with books about the planets, and this has happened within my career. And right now, as I'm retiring, what we're looking for is life on other planets. That's the buzzword. When I was building cameras and going to Mars in particular, we were looking for water, because water is the basis of life. Now we know where the water is. And the question is there life associated with it? A lot of the water isn't necessarily easy to get at. It might be ice, for instance. Okay, so, of course I can't read the darn thing. Just a minute. So, First project I worked on was the Pioneer 1011, and that was a big deal for the university. We were the people with the pictures. And so we processed them, we put them out. We had 2 or 3 computers on campus at that time, so it was a little bit slow, but we got things going. And then after I graduated, I did take a tour of India that took 6 months, and I came back determined to be a gemologist. But to be a gemologist required going to school again, and it required money. I was broke. So in order to pay for my new career in gemology, I went to work across the street at Space Sciences and stayed there for my entire career because we started a mission called, an instrument for a mission called the Pioneer Venus, and we built a probe that was going to go down through the atmosphere very slowly on a parachute and measure the properties of the sunlight coming through and the reflections from the surface. And that was so interesting that then I stayed on as Pioneer 11, flew by Saturn, and then I was pretty much hooked and never left. So in the 90s, we had Galileo's probe entering Jupiter's atmosphere, and then the big break for me came with the imager from Mars Pathfinder, which I'm going to talk more about, and the descent imager that landed on Titan. There was a huge success with Pathfinder in '97, which was the first lander on Mars since the Vikings in '76. So it had been a big gap. And that was a huge success. The next mission, the Mars Polar Lander, crashed. Huge failure. So I went from my career going up, big lab full of people, as you were saying, and then all of a sudden, with that crash, they canceled all the missions that I was involved with. I had nothing except, the department secretary and an empty lab. So I had to start over again. And we ended up proposing a mission to Mars called Phoenix, which was accepted, competing against 25 other missions. And I have to tell you, if you're going to get in the space business, get ready to compete. U of A is not the only ones in the business, and the proposals are really very spectacular these days. So you're going to, if you have a competitive spirit, this is a good field for you. Okay, so then the Phoenix mission was a huge success, and I'm taking too much time. I'm sorry. And then finally, we have across the street, well, I'm going to talk about these in detail, so let me skip that. What does it take to design cameras for space? Well, the camera you can buy at Best Buy is much more sophisticated than the cameras that fly in space. However, if you try, why wouldn't you fly them? And that's a good question. Maybe it'd work, but maybe it wouldn't work. And so would you risk a $200 million mission with a camera that might work and might not work? It would work great on the ground, but now you're outside of its environmental safety zone, so to speak. You're at colder temperatures. You have high radiation. You have the vibration of launch. You have all these other things going on. And your camera may very well fail. So we tend to build cameras we can totally rely on that aren't as sophisticated as the ones you can buy at Best Buy. I hate to say it, but that's the truth. So you have to define exactly what your requirements are, and then you have to stay away from any add-ons to those requirements. No high definition, or no high dynamic range, none of these things that you get in a commercial camera. We stay away from all those things as much as possible. We stay away from mechanisms because they tend to fail in space. We don't have shutters. We don't have focus mechanisms if we can help it. And we have very simple interfaces with the spacecraft and with other things that we have to interface with. Now in optics, you have to use rad-hard glasses, particularly if you're going to Jupiter. You can't cement surfaces together, which is commonly done on the Earth. And you have to really pay attention to scattered light and ghosts because you're out there where you're likely to be pointed near the sun, and boy, pretty soon all you're looking at is scattered light. We tend to go with the highest F numbers we can use, especially for landers, because without life on the surface, things aren't moving very fast, so you can have a long exposure time. And with a high F number, you have a great depth of field, and you don't need a focus mechanism. Now, if you're an orbiter, you're zipping over the surface pretty fast. You need short exposure time. You've got to have a very small F number. And we have to practice planetary protection and keep things clean. The detectors have high quantum efficiency. We use the anti-blooming. And you have to control the thermal properties of the focal plane. You want high signal noise observations, and so we go for the lowest noise possible and a wide range of exposure times. The instrument scales with the pixel size. So if you get too small a pixel, though, your dynamic range is very short. You have to tune each observation to fit in that dynamic range, or you have to take multiple exposures. So we tend to have an intermediate pixel size for that reason. And then everything's into the test program, and this is probably the reason we don't use commercial cameras, because the test program is really exceptionally difficult on cameras. Vibration, and this is the vibration of launch on top of a rocket, so it shakes pretty hard. And the thermal environments are exceptionally difficult. We often get down to minus 60 or 80 degrees, and most commercial equipment is not rated at those temperatures. And then there's the radiation environment of space, particularly near Jupiter. And we have to do the life cycle testing for any mechanisms. Are they going to, the bearing's going to freeze, the lubricants freeze out, all kinds of troubles. And then you have to calibrate and document. So a lot to do in the test program, and that's what takes most of the money. When I first started, we had a 1-pixel camera that we were flying. Basically, you took that pixel and you scanned it back and forth in a raster scan across the object while everything's moving, and so you ended up with objects that were, or pictures that were very strange and had to be reconstructed. So in the 70s, 1-pixel cameras for flyby missions worked just fine. We had great pictures. These are pictures taken with a 1-pixel camera. And these were the best pictures we had of these objects at the time. Now, in the late 80s, we proposed a camera that would land on the surface of Titan with the Cassini mission. And we were all the way up to a 1/8 megapixel camera at this time. And we built a multiplex system that could use several imagers using the same imager. And this was, I think, very clever. And you can see, is this a pointer? You can see these 3 cameras here. One's for looking down, one's for medium range, one looks to the side. So by using 3 cameras and spinning the spacecraft, we could get a 360 or a semi-hemisphere. No, that's a hemisphere, isn't it? We could get a hemispheric view as we descended through the clouds of Titan of the land underneath us. So this was the clever ideas we had. And, oh, I should point out, we actually, because we thought it might be dark down there, we put a lamp. So as we got close, we could light up the surface. And this is what the camera head looked like. There's 13 optical instruments crammed into something the size of a shoebox. This is a spectrometer system. This is the imaging system. And way too complicated, but we managed to get it all to work. This is what the imaging system looked like. The 3 imagers looking to get the hemispheric view of the surface. And what we were doing, this is a little screwy. Well, the PC has reconfigured my slide, but we used this CCD and divided it into sections. And so we multiplexed the CCD and used the different sections, and we accessed them using optical fibers. So we had a fiber bundle that was split between the 3 imagers and came back to 1 sensor. So everything relied on the 1 sensor. And we took pictures of the surface of Titan. Now, when these pictures came down, look at the river system here. Well, there's no water on Titan. The temperature is 90 Kelvin on the surface. So that's got to be ice. So what's the liquid that formed those river systems. It's not water. So we think it's some sort of methane-ethane mixture. So the surface of Titan is very strange. And people saw this picture. It looked like the coast of Italy or something. It didn't look like a different planet. And when you got on the surface itself, this was the size of the rocks. These rocks are made out of water ice, and they're the hardness of granite because of the temperatures they're at. And the other thing about them, you notice they're rounded. They've been eroded. These are river rocks. There's been a flow in this system. Very interesting. Okay, I'm going to jump ahead to Pathfinder camera. And I'm not going to read that list of attributes there, and you shouldn't read it either. But it's a stereo camera with 2 eyes. It's about the size of a Foster beer can. And notice it's kind of a happy camera. These are the air vent that let the air out is going up. It could have been a straight line, but what the heck. So, and it has eyebrows. The eyebrows are there because when you turn the camera and it rotates on this axis, there's a little motor, rotates up and down. And if you turn it straight down, the eyebrows protect it from dust. So just like, all right, well, I used to have eyebrows like you guys, but anyway, and then it had another motor here for going around. So it was standing about as tall as I am, and it could move its neck up and down, so it could take pictures of the whole, everything except straight down. So it was landed on the surface. These are the first images we got back in 1997. It had been 20 years since we had pictures of Mars. And these rocks are very interesting. They're only about this big. They look huge. We thought these were boulders, but when we found out the sizes, no. And there was an interesting hill back here that had what looked like a letter on it. It's sort of a Martian letter. Maybe it's a Martian university or something. So we could mess with the images and stretch colors. And this rock looks like it's 2 different colors, sort of like a 2-tone Chevy, you know, from the 50s. Well, it turns out that direct sun and illuminations from the sky are different colors. So if you stretch the colors enough, you can tell what's in direct sunlight and what's being illuminated by the skylight. And we drove a little rover around called Sojourner, and this was a lot of fun, and the public just loved this mission back in the summer of '97. It was a great year for the university. We'd won the NCAA championship. We've been waiting for a long time to win it a second time, but it's not happened. Maybe this year. Okay, I'm going to jump to the high-rise telescope, and I'm quite interested to show you some of these pictures. I don't have very many, don't worry. And this, I was the project manager for this. We developed a 0.5-meter diameter telescope. Is built at Ball Aerospace, and it is now operated from right across the street at the Sonnet building. Right across the street. They're getting 12 high-resolution images a day from Mars as they go in orbit. It's a polar orbit. And these images are enough resolution so that a pixel is about the size of a dinner plate. Now, how many pixels do you think there are on Mars the size of a dinner plate? How many dinner plates would it take to cover the surface of Mars? Well, it's a big number. And frankly, there's no way any one of you could ever look at all the pictures that have come back from Mars, even looking at them at low resolution. It's just so many, so much to look at. So you have to pick and choose your subjects to study. This thing has been going since 2006, been 10 years orbiting Mars. And even one picture, it takes like 35 screens just to see one picture. You have to keep scanning across and up and down and zooming in and out. Very difficult to even look at the data. So this is the era of big data already. And it's happening across the street. And this is an old slide. I think our number is up off the top of the chart now. But this Mars Reconnaissance Orbiter, that's what MRO is returning more data than you can imagine. And, well, here's what the telescope looks like in a drawing. Here's what it looks like as it's getting ready for launch. Here's a ray trace inside of it, and it's got a 3-mirror design to get rid of any kind of scattered light, for one thing. And it has a push broom. It's just a series of linear arrays, and in the center there's color. That's red in the center, blue, and infrared. So you get color in a little slice in the center, and the rest of it's red, and it just scans across the surface, and you have to read out the detector at the rate it's scanning. So there's kind of a tricky operations. The first thing they've looked at is all the detritus from the various missions we've sent to Mars, the parachutes, the heat shields, the spacecraft. They've all been seen, except for one. Mars Polar Lander has not been found with my camera on it. We've looked at the moons. Here's a picture of Phobos. Really a nice color picture. And then Mars is active, so they've actually taken pictures of things happening, like this is a dust devil, and that's the track that's formed behind it. We've seen avalanches in the polar region where there's a steep slope here. This is ice and layers of ice with various amounts of dust. And there's been a landslide, and you can see the dust coming up from the landslide. So Mars is an active planet. And in 2008, I was lucky enough to go through a whole competition for a mission. You could propose an entire mission to Mars. And this was an opportunity like none other. And competing against 25 other groups, including ASU up the street, we managed to win the contract to do what turned out to be about a $420 million mission, and to bring the operations center here to Tucson, which is here today and being used for another purpose now. And to show the interaction between our two U of A experiments, we actually could film the Phoenix lander as it's coming down through the sky to land on the surface of Mars. And there it is, blown up. You can see the parachute and the lander, and even the heat shield as it's dropped below on its way down. And there it is when it actually landed on the surface. So the U of A is really, kind of taken charge of Mars, I think. We're doing a pretty good job to cover the territory up there. We had all kinds of instruments. We landed in the polar terrain, which is thought to have ice near the surface. And we built a robotic arm camera. We had a robotic arm. In fact, let me just show that again. There's the robotic arm. Our whole purpose was to dig down and find ice. And there's the camera under here. And here's instruments on the deck. You could scoop up samples and put them in the instruments and do analysis. And that's the camera itself. The first thing we did was actually look under the lander. And when we did that, we were amazed that the thrusters had exposed the ice already. So here's the thrusters up here. And these are patches of ice where the thrust, the emission from the thrusters has pushed away the soil. And you can even measure its depth by the curvature of this straight strut as it comes over the edge. And it's 2 or 3 inches deep. And here's another exposed patch of ice. So there it is. There was a mystery, though, is what are these blobs on that landing strut? That caused all kinds of controversy. So here's a panorama showing the hummocky terrain caused by ice expanding and contracting with the seasons. And you can see one of the trenches we dug, we actually saw ice, and we could get samples of it and analyze it. These are pictures of the hummocks. Because we have stereo, we could make a terrain model. There's a terrain model within the reach of the arm, and we could guide our operations. These are the trenches we're digging all in here. So, fun experiment. We picked up scoopfuls of material. The robotic arm camera could focus, even though I said it shouldn't, but it did. And we saw white material on there. And then we had a microscope on the deck, and we could actually see the particles that were picked up in the soil. Okay, the last camera we're going to talk about is the OSIRIS-REx camera system. And this is operated from the same building we did the Phoenix mission from. It's about a mile from here. The university bought us a building to do operations. And after Phoenix mission was over, they're going, what are we going to do with this building? And for a while, it was rented out to Raytheon. But then we won another contract for an asteroid sample return mission. And now we're using the building again. It's filled with the whole new project. And hopefully, somebody in 5 years gets another project and will continue to use that building for operations. It's a really great facility that we have here. And I think we could probably arrange tours if anybody's interested, although not today. Very few universities have this sort of space infrastructure that we've developed here. Now, we had 3 cameras. I'll just go through this quickly. Here's the range to the surface of the asteroid. And when we're far away, we use the big 8-inch telescope. And as we come closer and closer, we can actually refocus it. And this is kind of clever, I thought, because we can take the telescope, and by this clever refocusing mechanism, we can turn it into a microscope. So out here, we're just detecting a star-like object in space. And down here, we've got less than 1 centimeter resolution of the surface. Resolution like this. So it's a pretty powerful instrument. And then we can do color mapping with our map cam and even focus down to sub-centimeter with color. And then our sample camera is used for videoing of when we actually grab a sample of the surface and bring it back to Earth. So 3 cameras. Polycam was built here in this department, and it's a 8-inch Ritchie-Chrétien telescope, has a focusing mechanism, and provides sub-centimeters imaging when we get to 200 meters. This is the kind of pictures we hope to get. This was a Japanese mission to an asteroid called Itokawa, and very strange features on it. Asteroids are not like planets. They aren't pulled into spheres necessarily. So I'm very near the end. Last slide. He's sweating. Not yet. Okay, good. Well, then I actually have 10 other slides. No. We have just found out that we're in a Phase A study. We've gotten a proposal funded, and we're going to try and build a lander camera to land on Europa, the second moon of Jupiter. Now, this is really a challenge because you're in the Jupiter environment, high radiation, so you have to prepare for the radiation. And it's an icy surface, so the ice is hard as granite again, so you have to collect samples somehow from this very hard icy surface and then analyze them with the idea of looking for life, because underneath the surface layer on Europa is an ocean, and that ocean could have hydrothermal vents inside that provide enough warmth and chemical ingredients that you could actually evolve life inside of Europa's ocean. And the ocean does somehow send geysers up to the surface sometimes, so there may be some of this material on the surface that you can look at. So we have actually partnered with 4D, the local company that has very close optical science ties, and we think we have the ability to actually see chirality. And chirality is a signature of life in the sense that some of the molecules are both right and left-handed, and life chooses, depending on what the material is, either the right or the left. So if you get an imbalance in chirality, then it looks like a life signature. So we're trying to build a camera that can actually see that sort of molecular asymmetry. So now when we write proposals, we are able to write them using the accomplishments from all those people here at the university who have worked on projects in the last 25 years. So we have a real basis for proving that we have abilities to make instruments of various types. And it's really up to the proposer to come up with the brain power to think up a new way to study these planets or look for life or look for whatever. I mean, that's the whole point. Find something new to look at. Right now, they've just funded 2 missions to asteroid groups, and one's a metal asteroid, which has never been seen up close, and the other is the Trojan asteroids, which, if you have Jupiter going around at plus and minus 60 degrees, there's a gravitationally locked, they're in the Lagrange zones, I guess, and they're gravitationally locked to Jupiter, so there's a bunch of asteroids there. And there'll be a mission to them. Many opportunities to participate in the existing missions, the ones that are just coming up to a start, like our Europa lander, and to work on new proposals. So if you're interested in space, and maybe you don't know you're interested in space, come and find out. And there's a lot of opportunities here at the U of A. We've been doing it for a long time, and we'll continue to do that. So thank you very much.